Good morning. We're here now for video number 4 in the K18 series looking at amplifier measurements. And in the last video we looked at some basics of DPD, for example, polynomial and direct DPD. So in this next video we're going to do some more advanced DPD topics, right Florian?
Yes, thank you, Darren. So, hello everyone again. In this video, we want to look at DPD again. This time, let's call it a bit more advanced topics. We want to cover two things here, namely the IQ averaging feature in K18, as well as a brand new feature that we have in K18, as well as on the signal generator, which is the so-called Crest Factor Reduction. For today, I will focus on K18D only, but everything that I'm talking about today, it also applies, of course, to the polynomial DPD. All right, so for today, the setup is pretty much the same as in the last videos. We have the SMW providing our signal. Different to the last time, I'm using a OFDM signal this time, and I'll explain you in a minute why. We're running the signal into our demo amplifier and we're analyzing it in K18. Because we want to look at crest factor reduction today, I did choose a stimulus that has a higher crest factor. If you look at the crest factor, it's 10.8 dB for this OFDM signal. It is not a 5G signal, but it's very, very similar to a 5G signal. So pretty much everything I'm talking about today can be directly applied to real 5G signal as well. The configuration of K18 as it is currently on my screen is pretty much the standard configuration. I did change some screens because we want to look at the spectrum and the ACLR today. And obviously, when we look at DPD, we're interested in the nonlinearity. So I have AM/AM and AM/PM open. And basically, the only thing that I changed from default is in the ACLR settings, I did configure them according to my signal. So I'm using a 98 megahertz channel and a spacing of 104 megahertz. There's no specific reason for that. It's just for the demo. And what I did switch on is the auto adjust acquisition bandwidth, which basically means that K18 uses a higher sampling rate than it would normally do for just analyzing the EVM and the channel itself. So let's have a quick look what it is. It's 382.5 megahertz compared to 122.88 megahertz that my reference signal has. So that's pretty much the only difference from the default configuration here. And with that, I guess we're good to go for some DPD. So as explained, we have the spectrum display here, and we have the ACLR result summary here. A quick note, because you might see some difference during the measurements. What we see here in the ACLR result summary does not necessarily correspond to the measurement trace in the spectrum FFT. And I'll come back to that later when we do IQ averaging. So, as you can see, we are driving the device under test into compression. This is the AM/AM compression up here. And obviously there is significant compression in the phase plot. And I would say, let's just start and see where K18D gets us to. Maybe keep the EVM number in mind, roughly 2.8%. And we are making a start ACLR-wise from around about 40.5 dB. So all I'll do is I'll hit start direct DPD. And direct DPD is basically configured to run 5 iterations. I'm in run single mode to optimize the video performance, so I have to do another run single once the DPD is done. And we can see a significant improvement, a little more than 2 dB in ACLR and, well, more than 1.5% in EVM. So, okay, we do have some improvement. Let's have a quick look at the ACLR in the spectrum analyzer mode. And we can already see, well, the ACLR we are measuring is probably, well, the shoulders definitely have an influence on the ACLR measurement. So what I'm going to do now is, in order that so that we can compare results later on, I'll just do a trace copy. So trace number 2 is going to be our direct DPD result. If you look at the spectrum plot here, there's, well, on the right-hand side, we can see that the, let's call it shoulder, is pretty flat, where we have a slight slope on the left-hand side. What does that mean? Basically, if the shoulders are flat, it means it's more or less noise that we're looking at. And as long as we still see a slope here, it basically means there is still some non-linearity, intermodulation, causing the shape of the shoulders. Now, if I turn off DPD, make another sweep, you can see there is a lot more intermodulation visible here. And because of the fact that with DPD, it's pretty flat here, at least on the right-hand side, I do suggest that we at least try IQ averaging. I think most of you know IQ averaging. IQ averaging basically is averaging the in-phase and the quadrature components of the baseband signal separately. This is only possible because what we have in K18 is basically coherent captures. The captures are coherent because we do a synchronization. Obviously, we do not have like a coherent setup where the source and the analyzer are coherent, phase coherent, but we do have a piece of DSP that does the synchronization to the reference signal. And as a result, we do get quasi-coherent captures that can be averaged in I and Q separately. The big advantage of doing this IQ averaging in I and Q separately is that in theory, you can cancel out all noise effects completely. In return, if you remember the averaging functionality of an RMS detector or of trace averaging in the spectrum analyzer, we are talking about magnitude averaging. And there, of course, you cannot average out noise, but you can just average it to, well, to its average value. So you get rid of peaks, but you don't get rid of the noise in general. Right, so let's activate IQ averaging and just do a measurement. You can see that the FFT spectrum at the far ends, to the far left and to the far right, decreasing with the average counter. But the closer you get to the signal itself, you can see that the trace stays pretty constant, which is what we expect since the intermodulation result does not get averaged out. And at this point, I want to get back to what I said in the very beginning, that the numbers we have in here are not calculated on the trace being plotted in the spectrum FFT plot. There is a very easy reason for that, because typically, if you do comparisons on ACLR, the reference is typically the spectrum analyzer, and the spectrum analyzer doesn't have IQ averaging. That is why we also do not calculate ACLR on the IQ average trace, but on the raw capture. Obviously, we would get better results if we would calculate it on the IQ average, but since people are comparing it to the spectrum analyzer, we made a decision to not calculate it on the IQ average trace. Right, IQ averaging is on now. And with that, we want to start another DPD series. As you can see, as the DPD and the IQ averages proceed, slowly the ACLR as well as the EVM is decreasing. The EVM is decreasing and the ACLR is getting better. Let me put it that way. Both are getting better. And once we're doing the final measurement, after the DPD is completed, we can see we're around about the same range ACLR-wise, maybe a dB or so better than before, and we are significantly better in the EVM reading. Now let's have a quick look at the spectrum analyzer. Let's do a run signal here as well. And now we can clearly see the difference. There is definitely a difference here. If you compare the yellow trace to the blue trace, we have, well, I would say 2-3 dB improvement in the shoulders. So why don't we see it in the ACLR result? The answer is fairly easy, because we still have this close-in, well, intermodulation or signal shapes that is still influencing the ACLR here. And there's another reason that I'm going to show you in a second. I will just do another trace copy so that we can compare all different results afterwards. So there is now, the blue one was direct DPD without anything. The green one now is direct DPD with IQ averaging. And as I said, it's not only the signal shape itself, basically the original filter, that causes the ACLR to not further drop, but it's also the artifact that you can see up here, the hard clipping, which is a key characteristic of the DPD as we're doing it in K18. Now, we did talk a little bit about gain expansion last time, which would be one thing that we could try here. The other thing, what we're trying, or what we're doing now, is we will apply Crest Factor Reduction. As I mentioned in the very beginning, the crest factor of the signal we're looking at the moment is over 10 dB. It's 10.7 or something, very similar to a 5G signal. And if we look especially at the EVM value that we reached here, 0.5 is an excellent number, but typically the thresholds we're looking at is definitely higher. So in the end, what we really want to do is we want to trade in EVM for ACLR. So we want to get lower in ACLR, and we can pay in EVM for that. Okay, let's give that a try. So I'll switch off the DPD. And in the next step, what I'll do is I'll go to reference signal, and a little bit hidden, there is a tab called CFR, or Crest Factor Reduction. So this tab is basically only a user interface. It's a user interface for a feature that we have on the SMW, the signal generator. It's option, give me a second, it's option K548 on the SMW, which is the Crest Factor Reduction. On a side note, it only works in ARB mode, but that should in general not be an issue. Since for those of you who have noticed, K18 now has a switch in current generator waveform that forces the SMW into ARB mode. So basically what it does is, assume you're in 5G mode and you hit ARB and read from generator. It will generate the waveform, load it into the ARB on a generator, and then just replay it from ARB rather than from the real-time mode. And once you have done that, you can always also apply Crest Factor Reduction. Right, so all we're going to do is turn it on. We'll put in our numbers, the 98 megahertz, well, I think it was 104 megahertz channel spacing. Why do we have to put in these numbers here? Because the algorithm that's being applied to the signal is simply a clipping and filtering algorithm. So what does that mean? Here I specified a crest factor delta of 3 dB. That means the signal gets clipped to, well, 3 dB or a little more than that. And then thereafter, it gets filtered to especially the, to whatever you enter here. And you should enter the signal bandwidth here and the channel spacing there, because it defines the filter shapes. Obviously, if you clip a signal, the spectrum gets wider. That's why we need the filtering. However, when you apply the filter, the crest factor changes and it typically increases again. So this is why this entire algorithm is applied in an iterative way. So you can also specify the maximum number of iterations. And obviously it can happen that we cannot reach the desired goal, then you'll get an error message. So once we have configured all our parameters for CFR, the crest factor reduction, I'll simply hit apply on generator, which will automatically apply the crest factor reduction on the signal. For those of you having a look at the signal generator and trying to figure out why the crest factor reduction state is off, there's a very simple reason for that, because we create the pre-distorted waveform and load it into the ARB. And here is why. Because the next step in our process is that we want to run DPD. And when we run direct DPD, we don't want to compare the crest factor reduced signal to the original signal, because the result would simply be that K18D reverses the CFR mechanism. So internally in K18, for the DPD only, we use the CFR signal as the reference. So keep that switch in mind, because it's very important to set it to the right position depending on what you're doing. So we want to do DPD again. Now on the signal with crest factor reduction on. On a side note, K18 also shows you through a warning that the current reference is the crest factor reduced signal. Because as we'll see later on, this has a significant influence on the EVM reading. you can already see that the EVM goes roughly down to the same numbers as before, significantly below 1%, but the ACLR is significantly better now. Now with the last measurement, you might have noticed that the EVM goes back up again to, well, quite a significant number compared to the 0.5 or 6 or whatever we had below 1% before. Before we look in more details on the ACLR results, I want to show you why the EVM changed to what you saw during the DPD algorithm. If you go to the CFR dialog, you see that it automatically switched back the reference to the original one, because once the DPD is done, for sure we want to do the EVM measurement and compare it against the original signal. And now basically you can already see exactly what we were trying to demonstrate is we did trade in EVM now for ACLR. So our ACLR reading is now in the order of 48 dB. However, the EVM reading is now worse than before, where we only applied IQ averaging. So what we did is we did trade in EVM for ACLR. And if we look at the result in the spectrum analyzer, we can see that the main change basically happened here next to the transmit channel. And it's basically a combination of, well, shaping the signal, I guess. And if we look at the resulting AM, you can also see that there is only a very few points are hard clipped here, right? And obviously, the more, or the clipping up here, which is the horizontal line that we had before, is basically the part that is responsible for, well, ACLR, for out-of-band emissions. And as we have seen, the Crest Factor Reduction helps us to move more points to below that clipping point, which in return gives us a better ACLR at the cost of a higher EVM, obviously, because the high amplitude values that are up here in the AM plot, they're definitely up here there in the reference signal. And basically moving them down here in amplitude obviously causes an EVM. But it's not a significant error, as typically we're talking only about a very few or a low percentage of points that lie up here. The majority, as you can see in the color indication, is up here. And since this area up here is all blue, we only changed a few samples. So with that, I think we conclude today's video. We have seen the effects of IQ averaging, which basically helps improving the ACLR result if the ACLR result is dominated by noise. And we have also seen the effect of crest factor reduction, which is especially helpful if we have signals with high crest factor. And the crest factor reduction primarily trades in EVM for a better ACLR.
Okay, great. That's fantastic, Florian. Thank you for going through that. I actually just realized at the end of the video, I didn't ask you any questions today. So maybe what I need to do is take some questions from Jam and we can pose them in the next video. What do you think about that?
Sure, let's do that.
Yeah, why not?
Sounds good.
Okay, great. So with that, we'll call this video an end and wait for the next one.